Okay.
Firstly, thank the organizers for giving me this great opportunity to present our work about monopole harmonic orderings in wire semimetals. So let me first thank my collaborator, Dan Halden at Princeton. This work started when I was a postdoc there, and then gradually getting developed with my students, Eric Barbaro and Canon Son. And then we also thank other people for great help in discussion, especially the future collaborations, etc. And we also thank organizers for providing us great fruit and should add in the ice cream in the last session. So yeah, before going that, because this is the last talk, I want to invite everyone to play the sum trick with me. And everyone here is an expert doing topological physics, but with a classical analogy of topological states, it can be exhibited quite quickly. So just as our president did, you can just sum up. And then the question, the rule of playing this is saying you are not allowed to rotate with respect to your to this axis. You need to keep your sum fixed as perpendicular to your arm. And then the question is, could you go from this position to this position without directly flipping around your arm? So, but you're allowed to move a little bit. So that's some trick. And you guys, if you want to give a stretch, you can start to 2 minutes. You can have a try and see if you can get some results. The
goal is to
don't go too much. You only need to rotate pi over 2.
Pi over 2.
You want
Organizer going to give us the answer. Okay, perfect. So that's exactly what Jen did here. So you first raise your arm here this way, and then go this position, and then go back. You magically rotate your arm, your thumb by pi over 2 without directly twisting. That's because our shoulder is quite flexible. We're quite flexible object, so don't need to catch it. And this pi over 2 is actually the solid angle spanned by the trajectory of your hand. So the quantum version that everyone familiar with is the Barry phase. And for a quantum state, once it's adiabatically evolving in the parameter space, you can pick up a non-trivial phase. And this phase is a monopole charge, corresponding monopole charge times the spanned solid angle. So in the most generic case, a two-level system, B dot sigma, and then in this case, monopole charge equals 1/2. So different from classical word will correspond to the spin 1 case. So now let me have an overview of our what I would like to share with you. So firstly, we learned that for superconductivity, it could be the symmetry is crucial, and the symmetry usually classified based on the spherical harmonic functions as S wave, P wave, D wave, and etc. So the question right now is there another part of this? Is this classification complete or not? And we have demonstrated the geometric phase. And the question is, here I only use the one single hand. So you have used both hands to do this. What's the result? If many hands, then what's the result? So what's the geometric phase for a two-particle state or many particle states? And then also, there are already nice talks about wire semimetals, and talks also talk about superconductivity. But the question here I would like to put, after imposing superconductivity, what's the fundamentally different state we can get? So putting these 3 ingredients together, that's what we're trying to propose. That's the monopole superconductivity, which is in a general sense, that's the class inside topological superconductivity that is distinguished from all the topological superconductivity that we have discussed, we have discovered so far. And in the particle Hall channel, we can also have similar things happen in the density waves, the charge density waves or spin density waves. And in total, themselves form the monopole harmonic ordering, and these are part of this topological many-body ordering, and the realization I will mention at the very end is possibly in biosemimetals. So as we know that in the mean field theory, the superconducting autoparameter coupled with the superconducting creating operators and give rise to the pairing Hamiltonian, and the superconductivity is distinguished based on the gap function symmetry of the gap functions. Usually what we're familiar with is if you have a perfect spherical Fermi surface and always do partial wave decompositions into S wave, P wave, D wave, F wave channels. And so for example, the S wave we have already known, that's the first known example of superconductivity. Mercury was discovered first in 1913, and then by BCS, well described by BCS theory. And then we could also look at superfluid pairing symmetry, for example, in helium-3, as for example, giving rise to P-wave type pairing symmetry. And we can also look at D-waves. The famous example is the height-C proof rate. For example, here it shows dx squared minus y squared wave symmetry. So which means the gap function is distribution defined over the Fermi surface. If you rotate the system by 90 degrees, it forms a non-trivial representation or rotation group that pick up non-trivial sign, and that's rotation. So, furthermore, recently people discussing the interesting topological superconductivities. Here I'm focusing on 3 dimensions. So for helium-3A, that's a typical example of px plus ipy pairing symmetry, which breaks time reversal, and the topology is characterized by the non-trivial phase winding around the gap nodes. And for helium-3B case, it's time reversal invariant. It's fully gapped in 3D, and the topological number is characterized by the real D vectors over the Fermi surface, forms the like Skyrmion type pattern, and characterized by the punctuality number of this real D vector over the Fermi surface. And here we are focusing on the monopole harmonic superconductivity, which could be realized in time reversal broken biosemimetals, the magnetic biosemimetals that Bing Hai and other speakers mentioned earlier. So it could give rise to a fundamentally new topological class of nodal pairing with non-trivial total vorticity, and this nodal superconductivity and nodal ordering, it will be independent of specific pairing mechanism, which is different from the known case. So, and here, because of broken time reversal symmetry, so D vector is actually intrinsically complex and is characterized by the Chern number over the Fermi surface. So, as an overview, so let's first compare this monopole superconductivity that I'm going to talk about with the known helium-3A case. In helium-3A, we know that it contains 2 nodes, let's say, over the Fermi surface in the momentum space, one at the north pole, another one at the south pole. So at the north pole, it forms P plus IP, at the south pole, it also forms P plus IP for one single spin component. And now, because the normal direction of the Fermi surface at these 2 points, north pole and south pole, are opposite to each other. So now if I count the winding on my autoparameter phase relative to the normal direction of my Fermi surface, then one picks up positive 1 vorticity, another one picks up minus 1 vorticity. So the summation is always 0. And this is true for all the known unconventional superconductivity that we have discussed so far. And now if we look at such a new superconducting autoparameter, so you will see, first you will see a new good quantum number which corresponds to the monopole charge of the Cooper pair. And it's characterized by, for example, most generic case can contain 2 nodes, very similar to what you found in helium-3A over one Fermi surface. And as one node of the Fermi surface, it can still exhibit P plus IP type superconductivity, but at the south node, approximately the superconducting pairing symmetry is Px minus IPy. In this way, it picks up non-zero total vorticity over one single Fermi surface, which could be realized around a wild point. And then And then now let's, so this result, this is actually a result of non-trivial Berry flux that need to go through the Fermi surface and giving rise to these nodes in the order parameter gap function. So for example, let's have a look at how to set up this question. Now we're no longer thinking about a single particle Berry phase. Instead, we're looking at a pair Berry phase. So, a specific situation that I'm discussing is, for example, I have two Fermi surfaces related by inversion symmetry, but with broken time reversal symmetry. In such case, I can have the scenario that the two Fermi surfaces can have two different trend numbers. And then now, if I start with inter-Fermi surface pairing, one with momentum k particle here, another one with a state at minus k here, and then I can form a two particles pairing state here, and then following similar definition as the barrier connection for a single particle state, now I can similarly define it for a Cooper pairing state here. So, so now you can see that I can, because the two particle pairing state is just a tensor product of a single particle state, so it gives rise to the, so if you take derivative by parts, you can decompose this pair barrier connection into single particle barrier connections in this way. And because these two Fermi surfaces with positive or negative helicities are related by inversion, so you can find that this contribution from each of Fermi surface actually adds up together. So give rise to non-zero barrier connection when one Fermi surface, for example, here carries chain number 1, another one here carries chain number -1. And similarly, the corresponding monopole charge for this core pair also get doubled from this single particle monopole charge. So, so for example, for here, the chain number equals 1 corresponds to monopole charge equals 1/2, and then the Cooper pair carries the monopole charge 1 here. And then we could prove that based on this non-trivial Berry phase, if we look at the total vorticity over one Fermi surface, and then so that is just 2 times the monopole charge of the Cooper pair. In another way, once my Cooper pair carry non-trivial Berry phase, this superconducting gap function must be nodal, and different from all the nodal superconductivity that we have discovered before. And here I will skip a little bit, not show you explicit model Hamiltonian, which is quite simple. And then, so basically we take a time reversal breaking via semi-metal and proximatized by S-wave superconductivity in the model. And what we obtained is the gap function is always nodal. And in one case, we could get, say, at the North Pole and the South Pole, each of them pick up a non-trivial vorticity 1 and adding up to be 2. And I can also change the proximatized superconductivity to give rise to another pattern of the vortex in the momentum space in the gap function. And then you can see that the total vorticity over one Fermi surface is always conserved as 2, where 2 is 2 times the monopole charge of the Cooper pair 1. So, so here we can also define what we call as the fundamental nodes, which contributes directly to the total vorticity. On top of that, you can always add the nodes in the gap function with vorticity +1 and -1 coming in pairs, like in And the interesting thing here is, of course, whether this pattern will finally be determined or this one will be preferred depending on specific pairing mechanism, and this like different symmetry of the pairing function under one single big topological sector, different from what we have done so far. So, so what is how to characterize the gap function in this system? So we know that here we found its monopole harmonic functions because in the presence of a Berry connection for this Cooper pair, the angular momentum operator first needs to be modified to include the minimal coupling and add another term in the radial direction proportional to the monopole charge. And we know that the spherical harmonic functions are the eigenfunctions of usual angular momentum operator. And when the angular momentum operator gets modified because of the barrier connection, the eigenfunctions also get modified to include this monopole charge Q and carries non-trivial singularities. So one of the features of this monopole harmonic function is its partial wave channels is always starts from the absolute value of the monopole charge Q. For example, when Q equals 1, and then you will not see L equals 0 channel. So there's no S-wave analogy of the in this monopole harmonic functions. It starts with P wave like, and then it looks. So you can also see, for example, here I just plot the magnitude of the of this monopole harmonic functions. It breaks the inversion symmetry and can give rise to, and it always contains non-trivial phase winding around these nodes. So, furthermore, if we look at the low energy excitations nearby each node, actually give rise to an emergent biofermion, but in the Nambu space. And for example, if we expand the original BDG Hamiltonian around the North Pole here, it gives rise to P plus IP type superconductivity. If I expand the BDG Hamiltonian around the South node, I would obtain P minus IP type superconductivity. And this Majorana while monopole in this momentum space give rise to the vertex of the gap function over the Fermi surface. And here you can see that the topology threads through all the energy scales. Although under a little bit doping, the original single particle wild points already in the high energy sector, but it still dictates the low energy physics around this Fermi surface. So now let's have a look at this surface spectra to further reveal its topological properties. For example, let's consider in this case, I have two Fermi surfaces, one enclosing the wild point with positive chirality at a momentum capital K0, another one with negative chirality at a minus K0. And then if I look at the surface spectra, before I imposing the superconductivity, I would first see the Fermi arc. So if I only see the surface spectra at one surface, I see a single Fermi arc for electron state. And because, BDG, because of BDG doubling, this also can be written, you can also get a whole Fermi arc state. Now let me turn on the superconductivity, and then I will see that away from the Fermi surface, my physics validate the Fermi arc states, and nearby the Fermi surface, I would see a mixture, a superposition of particle and Hall states because of this pairing. And then I will see this arc here correspond to the Majorana arcs connecting through the nodal points of my gap function and its projection to the surface spread zone. So for example, if I take a single cut as a fixed KZ between these two Fermi surfaces, I will see single particle physics as a double, BDG double of the Fermi arc states. And then if I take another cut, KZ, nearby the Fermi surface, inside the Fermi surface, nearby the North Pole, then I will see, because remember I said around North Pole, the superconducting order parameter is similar to P plus IP. So I will see a positive chirality Majorana state going up. And at the zero energy, you can see the Majorana state. And then if I take another cut nearby the South Pole, because remember the superconductivity there is like a P minus IP. So I get the chirality of my Majorana state here get flipped. But between cut 2 and cut 3, the system is not gapped because the nodes only happens at the North Pole and the South Pole. So the overall trend numbers remains the same. Trend for the BDG Hamiltonian remains the same. And if you calculate this by adding up, so if I have by adding up the chirality crossing this zero energy, so get a +1 here, -1 here, and a +1 here in, so that the Chern number is always the same for this system, for between these two nodes. And similarly, I could obtain other patterns for other patterns of the nodal points. So how to connect it to real materials, as we know that the time rules of breaking via semimetals were initially proposed as the earliest example of realizing via semimetals in the early theory papers. And later, Leon Valens and also proposed by a heterostructure of topological insulator and the magnetic moments can give rise to via semimetal system. For example, in Vanderbilt's group also proposed in BCC ions, we're very familiar with, also dozens of ion points. And there are also, for experimental realizations, first proposed, I think, by Kava's group, and in intervallic magnetic bismuth system, where the magnetic moments from magnets forms antiferromagnetic ordering, but with a little bit canting. But this material is still under debating whether it's a biosimilar metal or not. And they also proposed in magnet 3-tin system, for example, as mentioned in Deepak's talk, and based on the anomalous Hall effects and first principle calculation led by Deepak and Claudia Fesser. And as we, the speaker this afternoon mentioned that there are also recent science papers realizing initially it's original proposed by Bernevik's group in the cobalt-based Husler compounds. So by using RPARS and QPI experimental approaches to verify this interesting time reversal symmetry breaking biosemimetals. So now we propose if we could realize the superconducting time reversal breaking biosemimetal, then if I put these two identical superconductors together, then the Josephson current will have contribution from the zero energy Majorana modes. And if I change the, if I change the Weyl superconductor between this, if I change these two Weyl superconductors to be parity pairs, then I could get a pi shift in my Josephson current, which also in the energy phase relation also shows the 4-pi periodicity. And now let me use, how many minutes do I have?
I mean, essentially we're approaching the end, but
okay.
You could take a couple more minutes, yeah.
Thank you. So we can also generalize the idea to the particle Hall channel to look at, for example, the charge density wave or spin density waves. And in this Hamiltonian, similar as before, but in particle Hall channel, we could also define the particle Hall type Berry phase. And then when this charge density wave carry non-trivial Berry phase, which could be realized when the nesting vector connecting the Fermi surfaces of the the electron pocket and the Hall pocket enclosing via points of the same chirality. Then in this case, the charge density wave order parameter carries non-trivial Berry phase, and similar things could you could see similar patterns. So, for example, if we take this type of model Hamiltonian, which contains 4 wire nodes as a -1 + 1 -1 + 1 distributed inside the Green zone, and the nesting happens between the first and the third wire point, also between the second and the fourth wire point. And then in this case, you will see that the gap function is the gap function for the charge density wave is no longer the spherical harmonic function at low energy, but giving rise to the monopole harmonic symmetry. And similar as before, now if we look at the energy spectrum, so if I take different cuts around the Green zone, so if I between the two if I between these two Fermi surfaces, what I observed is the doubling of the Fermi arcs here. And here, if I take a cut inside this, going through this Fermi surface, and then I would see a non-trivial surface state with superposition of a state at electron state at k and the electron state at k plus the nesting vector q. And I can have an analogy of the Majorana state at zero energy. And this is quite interesting novel quasi-excitation, quasi-particle excitation. So as a summary, so here we like to say we found this monopole superconductivity, which is intrinsically nodal as dictated by the topology and the monopole charge of this Cooper pair. And it can also have a particle Hall analogy as the monopole charge density waves. And it belongs to a new type of many-body ordering and could be potentially realized in ion semimetals. Happy to discuss with you details. Thank you, everyone.
All right, questions, anyone? Yeah.
Is there some effect that depends on the via node separation, like the Fermi surface separation, just like in the normal vials, you have like the anomalous hole depends on the here.
Right. So here is very different. So here, maybe I can use.
Or yeah, I'll move.
Doesn't matter, like yeah, doesn't matter where Fermi surfaces are. When you say
No. So you can start with a single one point here and another one point here, and then you dope your system. Right? So now this original wire point already away from your Fermi surface. And now, say for example, looking at the superconductivity case, this is momentum k equals 0, and then I have its BDD pair here, and I have this BDD pair. So usually in S-wave superconductivity, because of the pairing, this gap would be opened up. But here you would see that at low energy, this part, it is always, the gap function is always nodal. So actually you can see that the original wire point already moved to high energy, but still dictates low energy topology. So it doesn't matter if it's a little bit away from the wire point. Which I like that, because that gives me more decimal sticks to
yeah, I guess I mean, like, you drew at the beginning two via nodes are separated in momentum space. Right? And that in, if you forget about superconductivity, that shows up in a response in a magnetic vial. It shows up as a Hall effect.
Right.
That depends on the valence separation.
Right.
So I was wondering whether, let's say you tune.
You still have it.
There's nothing new, like there's just this Hall effect, and there's nothing. Like, is there a thermal current or something like this?
Yeah. Okay, very good. So here you will see, for example, let's look at the surface state. Yes. So this arc is still Fermi arc. This one is like this whole pair. And then these arcs are Majorana arcs. These are chiral can be with different chiralities.
Right.
And then, so this, you can imagine this Majorana arc may contribute to the Summer Hall, and this arc still contributes to usual Knauss Hall.
Yeah, another question, Ben?
So we did, so when we did some sort of work related to Barry's talk earlier, maybe the first talk or the second talk, we actually had some file points that were linked by a CDW. The actual charge density rate wasn't, everyone's like, oh, what's a CDW wave vector? It wasn't like there was a single vector, it was like there's a complicated pattern of modulation that linked all these Weil points in momentum space. Have you looked at anything where you have patterns of like 4 Weil points related by 4-fold rotation symmetry and things like this, like in a plane? Like some complicated 2D ordering?
So could you let me know the chirality of the
Yeah, so it
Weil
depends.
points?
you can have it alternating like a d orbital, or you can have them all have the same chirality depending on the way you do the
So
symmetry.
here, this monopole structure relies on, for example, you see the four electron and the hole pockets. It relies on, for example, electron pocket, first one and the hole pocket with the second and the third one, enclosing the wire points of the same chirality.
So same chirality, yeah, that's good. That's better, I think.
So if
Yeah.
it's different, then the charge density wave still carries zero barrier phase. It could be gapped out.
I see.
Let's say, for example, usually happen in inversion break files.
So you haven't looked at something where I have like 4 wild points related by just rotation symmetry in one plane, and there's some ordering that pushes them all that links all 4 of them in a symmetric way.
Mm-hmm. But what says you mean the full electron hole pockets, the nesting?
Yeah, like the nesting is more than just a single. It's like a C4 symmetric set of nesting
Oh,
vectors.
I see. You mean you
Yeah.
have both you have nesting vectors connecting both cases, one with opposite.
No, they all have the same, but it's not just one. It's so it's like we see something that looks like in the XY plane you have 4 wild points related to each other by C4 symmetry.
So you're saying something like a checkerboard pattern rather than
Well, it could be you can either those are sort of a free crystal momentum,
So
plus
what's
all
your-
plus. We can do both either way, so we can start with all plus, I guess. If that's what you want.
Oh, with
right?
all plus.
Yeah, that's what you want, right?
Oh, great.
And they're all linked. And the point is the
Right.
CDW is some complicated nesting that respects the 4-fold symmetry. So it links. So like what we see is something like that.
So that Fermi surface quite because
Like
the
it
system
nests
have
all of them together in a way that preserves the crystal symmetry.
Okay. But the crystal symmetry, I mean,
Like the 4-fold rotation.
we can discuss in
Yeah. So but you didn't
Sounds
do that,
Sounds
right?
exciting. Okay.
Okay.
But did you see nodal or not?
It's a CDW, it's not superconducting, so it just opens a gap. And it's
Is a CW nodal or Fermi nodal?
I mean we measure a gap in that sense, but I don't know.
Okay.
I don't know
Yeah,
what
we
you
can check.
measure in that sense. Yeah, we can talk.
Okay, so yeah, you'll talk. Then for now, are there any? That's good. Any other question? Yes, yeah.
You said for the vial fermions, there's a minimum of 1, right? You said like you never have S wave, you start at P wave.
For this case, for this type of case, if you want to go higher Chen number, you get higher.
Yeah, that was my question. If you went to higher Chern number, the minimum also shifts.
Right. So if you get higher Chen number, you would get, say, the total vorticity would be 4. For example, you have a Chen number 2 case, and then this total vorticity would be 2 times the multiple charge of the pair, and then that would be 2 times 2 equals 4. When the single particle Fermi surface carry Chen number 2. And then this time we have to look at the pattern of this vortex. So a guess is we haven't found, we don't have as many models as you guys have, but I'm happy to chat more with you. But I would guess these nodes would repel each other and form a tetrahedron in the Fermi surface. That'd be interesting too. And more exotic case, if you have a pairing between trivial Fermi surface with Chen number 1, then you will get multiple charge 1/2, and all the parameters will be intrinsically spinner. That can give rise to some exotic phenomena. Yeah.
All right. Any more questions, perhaps? Well, maybe I can ask a question as the chair. So you contrasted the nodes that come from monopole pairing with the helium A phase.
Mm-hmm.
So if you were to look at the Hamiltonian that describes the gapless quasi-particles around the nodes in the monopole pairing case, would that also just be described by a Weil Hamiltonian? Only you just have 2 plus Weil nodes, where they're in the helium A phase. So you have plus and minus, or does it take a very different form?
Yes, again. So here.
Yeah, this picture essentially. Yeah.
Right. So here's a projection makes a difference. Initially, say you have a pairing matrix in the up-down basis, spin up-down basis.
Yeah.
And now, at the low energy, at this Fermi surface only contains positive helicity. So I swap the basis from spin up-down to helicity basis and project out other three matrix elements in my pairing matrix and only get a pairing function. That function is a monopole harmonic function.
Yes, but as in the case here, where you could forget about spin there.
Right,
In
here I
this
just
case.
take one spin species, one spin up.
Yes. So and then you can look at what the dispersion of the low energy quasiparticles
Right.
is around the nodes. If you were to do that here, what would that look like? Like a Weil Hamiltonian or different?
Because here we just want to ask what's the low energy, because superconductivity naturally defines the low energy physics. So maybe I can see on the backup side. So the interaction is not singular, but once you project to the Fermi surface, to the helical Fermi surface, you get this interesting.
If you want, we can also do that offline.
Oh, that's right here. I'm sorry, so basically, the interaction. Yeah, the interaction is non-singular. As a usual case, you just do the partial wave decompositions. But here, we need to project it to the helical surfaces. This naturally shift your angular momentum and includes, because now it includes high angular momentum channels. If you start with say j equals 0, it automatically includes p-wave contributions, and then this function becomes monopole harmonic functions, all because of these projections to the different helical Fermi surfaces. I can tell you more.
Yeah, we can maybe discuss it in more detail. Yes. If there's no more questions, then let's thank you again.